Welcome everybody. Welcome to the 8th or 7th, I'm losing count, of these Fridays. Losing count for a good reason. I mean, it's very exciting to organize this. In this specific Friday, we have Professor Andreas Wallraff from ETH. I don't think you need much introduction, but these are kind of open sessions, and we have people also from different backgrounds. Andreas is one of the leaders in quantum hardware. This is what is called these days. In superconducting quantum hardware. We used to call it experiments a few years ago, and theory, now it's software and hardware. He will be talking about very recent works in executing deep quantum optimization algorithms in the superconducting devices they are building in ETH. He did his PhD in Germany with Professor Ustinov, then was a postdoc in Yale University, and after a short postdoc, basically he's been a professor for quite a few years in ETH. So Andreas, the floor is yours.
Good. So thank you very much. Thanks, Dimitris, for inviting me to speak at your session, and thanks for everybody stopping by to listen into it. So I hope you can all hear me and see my screen. So I'll talk about a quantum approximate optimization algorithm that we've implemented on a 7-qubit quantum processor that we have designed and manufactured at ETH and then also operate at ETH. And so here on this first slide, you see a picture of the device that this experiment was actually done on. And maybe I'll start with walking you through a little bit on what elements are on this device. So the yellow structures that you see that form this sort of double diamond configuration, those are the superconducting qubits. There's 7 of them. The superconducting qubits can be coupled to each other through high frequency resonators. So these are these turquoise lines that you see connecting selected pairs of qubits. Then every qubit can be controlled in 2 ways. So it can be controlled by applying microwave pulses. Those are applied through these pink looking lines. And then it can also be controlled by applying voltage pulses through the green lines that create currents close to a squid loop of the superconducting qubit to tune its transition frequency. And so for every qubit, these control lines are unique, but the qubits can be read out through a joint feed line, and that joint feed line you see in this purple line, one that passes along the bottom here, from the left part of the chip to the right part of the chip, and there's a similar one on the top. And this feed line passes by a combination of microwave frequency resonators that are hooked up to each qubit individually. And the resonator, which is used directly for the readout, is this red lambda quarter resonator. So it has a length of lambda quarter at the wavelength that we do the readout at. And that's not directly connected to the feed line, but through a so-called Purcell filter, which is another lambda quarter resonator. And this combination of readout resonator and Purcell filter allows one to perform high fidelity and very fast readout on these qubits, which is important, for example, in instances where you're trying to do error correction. Yeah, and so this is the device that will be the workhorse for this talk. So Dimitris already mentioned the title of the talk. So it's executing deep quantum optimization algorithms on a superconducting quantum processor. And this work was done by our quantum computing team in our lab at ETH Zurich. And the first author of the paper that goes along with it is Nathan Lacroix. He's actually a master's student in our lab who will soon start his PhD. And he was part of a team that involved a number of postdocs, and I maybe should single out 2 of them. That's Christoph Hellings and Christian Andersen, who worked with Nathan on this particular project. And at ETH, we have maybe a bit more than 10 graduate students and 5 postdocs and a few staff supporting us technically and administratively. Okay, so this is another picture of the device. We've discussed that already on the first slide, so I'll not spend more time on that. But beyond mentioning the main authors of this work, I should, as usual, mention everyone else who has moved through our lab throughout the past now almost 15 years. So there's quite a number of students and postdocs who've worked with us, and I think this year was a particularly successful one for our postdocs. So there's 3 new professors that I should maybe briefly call out. So Simone Gasparinetti now is an assistant professor at Chalmers University since May, I think. Pasquale Scarlino is a professor at EPF in Lausanne, which is the sister institution to ETH Zurich in the French-speaking part of Switzerland. And then there's also Stefan Philipp, who's been a postdoc with us a while ago and has been at IBM in between, but now is a professor at TU Munich and the Walter Meissner Institute of the Bavarian Academy of Sciences. So that seems to be going very well for many of them. All right, so this will be a talk in the context of quantum information processing and quantum computing, and I do think that there's currently 2 major challenges in quantum information processing, and one is clearly the holy grail of the field is to realize a universal fault-tolerant and therefore error-corrected quantum information processor. And that's an enormous challenge. It requires quite a large overhead in the number of qubits that you can use, that you need to use to implement the error correction. And until we can have algorithms implemented on many logical qubits that are error corrected individually, will probably still take a moment, and it will require us to increase the size of the devices that we're able to build and control. But this is also a direction that our lab spends quite a bit of time on, and we had a recent nice experiment that came out in Nature maybe a month or so ago on making a good step towards error correction by implementing a repeated error detection protocol using stabilizer measurements. A second goal of this whole field of quantum information processing is to use these mid-scale devices with maybe several tens of qubits to run algorithms on them to learn about how they perform and to develop strategies how these algorithms could actually go towards outperforming conventional computing systems in solving certain problems. And there was this breakthrough result from Google at the end of last year where they've demonstrated a quantum advantage, or have done this quantum supremacy experiment in their 53 qubit device where they have run a randomized algorithm that was essentially impossible to reproduce the results of on even the largest conventional computers that they had available at the time. Okay, and today I'll not talk about our efforts on quantum error correction, which we're continuing to work on, but talk about a recent experiment that we have done on a quantum approximate optimization algorithm. So my talk will come in these 3 parts. So I'll give a little introduction to superconducting qubits and circuit QED. I know that many of you probably know some of the background, but maybe not everyone. And so I'll gonna pick you up with providing some input in superconducting qubits and circuit QED in the beginning. Then the main experimental result that I'll discuss is our implementation of quantum approximate optimization algorithms. And in particular, the fact that we used an efficient continuous gate set on our devices to improve the performance of these QAOA algorithms, or of this QAOA approach significantly beyond using standard gate sets like single qubit gates and CNOT gates, for example. And at the end, if there's time, we can talk a little bit about the future challenges. Good, so I think many of you know about superconducting circuits and how to do quantum physics with them. Maybe I can keep this brief. So there's essentially 2 important degrees of freedom in superconducting circuits. One is charges. So for example, the charge sitting on a capacitor plate, and an individual charge in a superconducting circuit can be in a superposition state of being on either one of the 2 capacitor plates. And you can write this in this pictorial wave function if you like. Similarly, if currents flow through a loop, these currents will create a magnetic field, and the magnetic field will thread the area of that loop and thus define a magnetic flux phi. And also currents and fluxes can be in superpositions of flowing either clockwise or counterclockwise here in this way I've represented also as a pictorial wave function. And charge and flux are conjugate variables that are the dynamic variables describing the physics of any electronic circuit, as a matter of fact. And charge and flux are similar conjugate variables as position and momentum are for the motion of a particle in free space. And therefore, as you know, for position and momentum of a particle in free space, there's those obey a commutation relation or a Heisenberg uncertainty relation, and the same is true for charge and flux. And so these charge and flux conjugate variables are variables that you can use to express the Hamiltonian of any electronic circuit. And then if you replace in this Hamiltonian the conjugate variables Q and phi by their corresponding operators, the charge operator Q and the flux operator phi, then that defines a Schrödinger equation which you can solve and then find the energy levels of any superconducting or of any electronic circuit, for the matter of fact. Good. Realizing that, you can look at two very basic circuit elements that get used a lot in quantum information processing with superconducting circuits, and these are harmonic oscillators and anharmonic oscillators, or qubits. Yeah, this harmonic oscillator is a combination of an inductor and a capacitor. Currents flowing through the inductor create magnetic flux phi, and charges on the capacitor are labeled Q here. And the Hamiltonian for this circuit is quadratic in both flux and charge, and therefore it's described by this harmonic oscillator Hamiltonian. So typical values of inductance and a capacitance are such that the resonant frequency of such a circuit, when we realize it on a superconducting device, is typically on the order of a few gigahertz or maybe a few tens of gigahertz in frequency. So this harmonic oscillator then has an energy level spectrum with equidistant states that you can label from 0 to n, and their energy difference is then Planck's constant times the resonance frequency of that circuit. And that allows us to essentially create electronic versions of photons in our circuits, and then use these photons to either couple qubits to each other or send quantum information along transmission lines from one part of the circuit to the other part of the circuit. A second important circuit element is the Josephson tunnel junction. So if you compare the linear harmonic oscillator on top and this anharmonic oscillator on the bottom, you see that the linear inductor has been replaced by a Josephson tunnel junction represented by this box with a cross. And this Josephson tunnel junction is essentially an ideal nonlinear inductor. Instead of having the magnetic energy depend quadratically on the flux phi as in the linear inductor on top, here the magnetic energy depends as a cosinusoidal function on this flux phi that is generated by a current I flowing through that junction. And this cosinusoidal dependence of the energy on that flux leads to the situation that now the energy level spectrum is not equidistant, has not equidistant energy levels anymore because the Hamiltonian is not quadratic, but has non-equidistant energy levels. And you see an example of that on the right-hand side where the ground state is labeled G, the first excited state is labeled E, and the second excited state is labeled F. And the transition frequency from E to F is by an amount alpha smaller than the transition frequency between G and E. And these types of energy level diagrams then allow one to define a qubit. You could define the qubit subspace as the ground and the first excited state. And as we'll see later in the talk as well, the second and higher excited states are also useful, for example, for realizing 2-qubit gates. And the Hamiltonian for the superconducting qubit is shown here, where this second term describes the difference of the second excitation energy in comparison to the first excitation energy. There's another simple way how you can see this specific feature of, or how you can understand this specific feature of this energy level diagram of the qubit, of the superconducting qubit here, where the E to F transition frequencies by alpha smaller than the G to E. And this can be seen if you look at this diagram on this next slide here. On the left-hand side, you see again the LC resonator, where the energy of that system is plotted versus the flux variable. And the potential energy in this representation is quadratic in flux, which you see by this parabolic function here. But for the superconducting qubit, the potential energy is cosinusoidal in that flux. Yeah? And then if you calculate the energy levels in that cosinusoidal potential, you see that the energy level separation is going to get smaller as the energy of the different states in this potential gets higher, essentially because the cosinusoidal potential opens up towards higher energies, which then moves the energy levels closer to each other. Okay, so then there's different ways how to realize these superconducting harmonic oscillators. Electronically, you could either realize them as LC lumped element LC resonators. Yeah, so here on the top picture you see one where there's a meandering line that creates the inductor in the left part of the circuit, and on the right part of the circuit there is a interdigitated finger capacitor, and the parallel combination of these two creates a harmonic oscillator. You could also just use the modes of a hole drilled into a superconducting metal block, for example, as harmonic oscillator modes to store photons, or as you've seen on my title slide already, you can use coplanar waveguide resonators for doing the same thing. Or you could also use a superconducting qubit and take one where the cosinusoidal potential is very, very deep, and then at the bottom of this cosinusoidal potential, the energy levels are also in reasonable approximation equidistant from each other. And then there's a range of different superconducting qubits that are essentially all made from combining Josephson tunnel junctions with either capacitive or inductive elements. And here you see a few examples: the Cooper per box, the Transmon, which differs from the Cooper per box by having a much smaller charging energy, or various variations of this Hamiltonian with different parameters that people have chosen to give names to, like Xmons, for example. Or one of the graduate students in our lab called this nicely looking qubit a Jellymon some time ago. So we didn't use that in the publication, but we lovingly called it like that in our lab for a while. So there's many different superconducting qubits that people have built so far. So here you see a selection of those, and for example, you could do a little exercise for yourself and figure out whether you recognize these qubits and what they are and what experiments they were used for. Yeah? So some of those are quite famous. Quite a few of them are also from our own lab, and maybe they're less famous then. But maybe you can do it as an exercise, figure out what qubits are shown here. Okay, so then a question: how do you operate these superconducting circuits quantum mechanically? And so here's my little 3-step recipe. So here's a superconducting qubit with a capacitor and a superconducting tunnel junction. And that quantum circuit, you could investigate its properties in a similar way as you would investigate the properties of say, an atom. Yeah? In an atom, you would investigate its properties by shining a laser on it and then measuring the scattered radiation. So here we don't shine a laser on it, but we connect our qubit to a microwave source whose radiation, or the radiation of which we deliver towards the qubit through a coaxial line, and then couple it capacitively. And then we can look at the scattered radiation by connecting another coaxial line and an amplifier to that quantum circuit. And for doing that and maintaining the quantum coherence of the circuit, there's a number of things that you need to take care of to preserve the coherence. So first is to avoid the dissipation. So if you have dissipation in that circuit, yeah, that dissipation will lead to energy relaxation, and that you want to avoid. So you get rid of any of the resistive elements that might be in the circuit, and that's one of the reasons why you use superconducting materials. A second step is that you want to cool the circuit down to low enough temperatures. So maybe I omitted to say what the typical frequencies are, the typical frequencies are in the range of several gigahertz to several tens of gigahertz, and that you can convert to a temperature by multiplying the gigahertz transition frequency value with 50 millikelvin, and that gives you roughly the equivalent thermal energy for the energy level separation. So for 10 gigahertz, it's about 500 millikelvin. And so that means that you need to operate the circuit at much less than 500 millikelvin to make sure that the system is actually prepared in its quantum mechanical ground state and not in a thermally occupied state. And to achieve that, you put these circuits into a cryogenic system, and these are, since more than 50 years, a commodity that you can just buy and do your experiments in. And finally, maybe the most important aspect of it is that you need to be able to control the coupling of both your control circuitry and the readout circuitry to your superconducting quantum coherent part of the circuits. Because if the coupling there is too strong, excitations could leak from the superconducting qubits or the superconducting quantum circuits more generally, both into the control electronics, which is certainly unwanted, and also too strongly in the readout electronics. For example, if that was happening at a too large rate, it's maybe nice for reading out the qubit state, but if you want to maintain the qubit coherent, you need to control that coupling strength. And maybe here in this pictorial representation, you can do that by controlling the coupling strength by doing clever things about the size of this capacitor with which the qubit couples to both the control and the readout circuitry. Okay, and so by now this is really something that many labs have under control, and my estimate is that there's maybe now somewhere between 100 and 200 academic labs that work with the quantum physics of superconducting electronic circuits. And also there's an increasing number of both large IT companies like Google and IBM and others, and also a growing number of startups, both in the US and now also in Europe and in other parts of the world, that are building these circuits successfully at the scales of up to several tens of qubits. And the largest circuits that we currently know about are on the order of 50-some qubits. Okay, another aspect that is quite prominent in the use of these circuits is this idea of using superconducting circuits for mimicking this field of cavity quantum electrodynamics. And so you see a picture here where there's an atom in an optical frequency cavity made from two mirrors, and the dipole moment of the atom can couple to the electromagnetic field of a mode inside this cavity. And this is a useful feature because it allows you to interface atoms to photons. It allows also several atoms to interact with each other in the same cavity. You can read out the atoms by measuring properties of the cavity and vice versa. And a circuit version of that we had realized some time ago while I was at Yale. And this is now very useful in many different contexts. So where you replace the cavity by a harmonic oscillator and the atom by an anharmonic oscillator, and the effective dipole coupling you realize by coupling the two capacitively to each other. And in this way you can realize strong coupling between qubits and microwave frequency photons in these circuits. And it's relatively easy to realize and simple to fabricate and integrate. Overall much easier than doing any of the atomic physics cavity QED experiments, and that's also why you now see many superconducting circuit cavity QED experiments that people do. And from that basic idea, a number of research directions have developed. So first you can use these superconducting circuits then to study quantum optics or the physics of quantum optics. You can, instead of coupling superconducting circuits to microwave photons, you can also couple essentially anything else that has microwave frequency transitions to these microwave frequency resonators, and do so-called hybrid circuit QEDs, for example, with semiconductor quantum dots or with other atomic systems. And this is also very useful for quantum information processing and quantum simulation. And so why is circuit QED useful in particular? I've mentioned some of the reasons already. So another reason is that putting qubits inside a resonator or couple it strongly to a resonator helps to isolate qubits from their electromagnetic environment. They can have better coherences than if the qubit was just suspended in vacuum with nothing else around it. And this is possible while maintaining the addressability of qubits. Qubit states can be read out by looking at the resonance frequency of the resonator, so there's a quantum non-demolition way to do that, and that's very useful and used in essentially all of the quantum computing experiments with superconducting qubits. And you can also couple qubits to each other by sharing a joint microwave frequency resonator mode. And you can convert stationary to flying qubits and sort of essentially send photons from one qubit to another, either on the same chip or even between chips, and also between different cryostats if you want to. And this was really very successful as an idea, and I won't go through all these examples. So if you want, you can either look at the recording of this talk later and stop it at the slide to look at the references, or you could also ask me to send you a PDF file. So this is a collection of nice quantum optics work that has been done with circuit QED and superconducting circuits. And as I mentioned, you can also couple different other physical systems to superconducting circuits and their microwave photons stored in them. And something that our lab works on is semiconductor quantum dots, but this could also be spin transitions in NV centers, for example, or mechanical degrees of freedom, or a range of other systems are useful in that context. And as I mentioned, superconducting circuits fulfill all the DiVincenzo criteria for quantum computing, and essentially a very solid base of experiments have demonstrated that superconducting circuits are a prominent system to pursue quantum information processing. And I mentioned in the beginning that the two dominant directions are working towards realizing error correction and then looking into non-error corrected applications of superconducting circuits. And these non-error corrected applications maybe fall into two different categories. Digital and analog quantum simulations with superconducting circuits is one of those categories. And you could even think of simulating problems from chemistry and biology and simulating other quantum physical systems. And one of the aspects that people find very, very interesting is to use superconducting circuits to tackle quantum chemistry problems. And there's been a nice set of examples, many of which stem from IBM and Google, showing how you can run non-error corrected algorithms to learn something about basic properties of molecules, of small molecules, by simulating them using superconducting circuits. Okay, and so now we're getting to the meat of the talk, which is then the new part that probably most of you were looking forward to, is thinking about one of the non-error corrected applications of quantum algorithms in superconducting circuits, and then also other physical systems, which is the so-called quantum approximate optimization algorithm. And there have been a number of works before by different groups involving, also including Rigetti, and there's some experiments with ions, and a very recent experiment from the Google team as well. And we have thought about what we could contribute there with this device, with this 7-qubit device that I've shown to you on my title slide. And that's what I'll spend the rest of the presentation on.
Great. Thanks for the introduction, Andreas. As I said, the audience really appreciated it. We have quite a few students as well, and thanks for taking the time to, and looking forward for the main meet, as you said.
Good.
Cheers.
All right. So the next part then will be about this quantum approximate optimization algorithm. Yeah, and generally this algorithm presents a hybrid approach. Yeah, an approach that combines both evaluating a part of the algorithm quantum mechanically, but then also having a classical optimization algorithm helping the whole scheme to work. And the idea that I'll discuss here is to use that quantum approximate optimization to find approximate solutions to combinatorial problems. And we picked a particular combinatorial problem that is known as exact cover. But the first slide here is discussing more generally properties of this quantum approximate optimization algorithm. So one of the approaches that one chooses to solve a combinatorial problem is to map that combinatorial problem onto a so-called Ising Hamiltonian. And here you see that Ising Hamiltonian, it's written down as a number of spins that interact in this typical Ising fashion. And the first term describes this interaction between two spins I and j with an interaction strength jij. And the second term describes magnetic fields that could change the energy level separation of the individual spin I controlled by a magnetic field hi. And this has been theoretically worked on, and the approach how to map a certain combinatorial problem onto this Ising Hamiltonian has been well thought through, and you can then show that if you find the ground state of that Ising Hamiltonian, you actually can also find the solution to this combinatorial problem. And so then is the question, how do you find the ground state of this Ising Hamiltonian? And this QAOA approach is essentially stimulated by ideas about quantum annealing and a trotterized version of that, essentially. So here on the right-hand side, you see a circuit diagram where you consider capital N qubits on the left-hand side. And then you prepare these capital N qubits in an initial state, for example, an equal superposition state by applying these Hadamard gates. And then subsequently, you apply a set of gates to all of these qubits. And these gates are applied in different steps that are called layers. And each one of those layers is characterized by two types of operations that are applied to the set of qubits. So there's one operation that is known as a so-called phase separation operation that is described by this unitary here that is expressed, and that depends on this problem Hamiltonian that maps to the combinatorial problem that you wish to investigate. And that's done in this first step in this blue box that you see. And then there's a second step, that's the so-called mixing operator, UB, where you apply this Hamiltonian B hat through this unitary evolution to your set of qubits. And the combination of this phase separation operation and the mixing operation, that forms one layer. And then what you can then show, if you combine many layers with each other, then this the execution of many layers in the limit of the number of layers going to infinity is able to identify the ground state of this Ising Hamiltonian. And at the end of this execution of a large number of layers, you can measure the state of the qubits that is the result of applying this set of gates. And an aspect that I've actually omitted to say is that the set of gates that you apply here is parametrized by these values gamma and beta. And these parameters you see in the unitaries here, the parameter gamma is a multiplier to the problem Hamiltonian C, and the parameter beta is a parameter multiplying this mixing operator B hat. And what is important when you apply these gate sets in the quantum approximate optimization algorithm is that you optimize these parameters gamma and beta to minimize the problem Hamiltonian. And this minimization actually happens in the QAOA algorithm by performing measurements on the qubits and using those measurement outcomes then to calculate the expectation value of this problem Hamiltonian, essentially determining the energy of the state that you've created by applying the set of gates to the qubits. And then you run a classical minimization algorithm. Yeah, so you do say you have looked at two different sets of gammas and betas for your problem, and you're trying to then change gamma and beta in a way to minimize the expectation value of C. And when you find a minimum of this expectation value of C, you can identify the ground state of this Ising Hamiltonian, and in this way find an approximate solution to your combinatorial problem that you were after in the beginning. And the performance of this algorithm depends on the number of layers that you can execute. And theoretically, it has been shown that there's sort of an equivalent, or that you can show that you can reach the ground state if that number of layers goes to infinity. But that number of layers then requires execution time on your quantum computer. and you will run out of coherence of your quantum computer as long as you don't do error correction. And so figuring out what the ideal number of layers is that you should run your circuit for to approach the actual solution in the best possible way is a big challenge. And in our particular experiment, we've looked at this particular problem of the dependence of the performance of the algorithm on the number of layers which we have executed. Okay, so and let me get to the heart of what question we have looked into. So the key part in this execution of the QAOA algorithm is to run this phase separation unitary that is based on this problem Hamiltonian C, with the parameters Jij that define the qubit-qubit coupling and the bias field H that acts on every individual qubit. And for the examples that I'll be discussing in this talk, we'll actually neglect or will not consider examples that have single qubit bias fields. But thus that could be considered in similar ways. So one of the things to notice is that in this problem Hamiltonian C here, all terms commute with each other. And as a result of that fact, you can consider every individual term in the sum of this problem Hamiltonian individually. So you can look at these two qubit interactions and how you realize them one by one, rather than looking at all of those two qubit interactions simultaneously. So therefore we look at the interaction between qubit I and qubit J through this unitary here, which is based on the problem Hamiltonian C that you see up there. And this unitary has as its core part then here this exponentiation of the term Zi times Cj with a prefactor Jij, which is the coupling strength between the two spins, multiplied with this variational parameter little gamma. And so to implement this unitary here now, you need to be able to control this effective interaction gamma times Jij between the spin I and the spin J. And there's two different ways essentially to do that. A standard way to do that is to decompose this interaction into two C0 gates and a single qubit gate. And that's essentially shown here. So on the left-hand side, you see qubit I and qubit J. So the two lines here represent the qubit states. The line with the green dots on is a C phase gate. And the C phase gate combined with two Hadamard gates essentially forms a C0. And there's a second C0 on the right-hand side here. And in between these two C0s, there's a single qubit Z gate that then essentially realizes this unitary here. And you see, for doing that, it requires two C phase gates, four Hadamards, and a single Z gate. And what we've thought about in our experiment is actually how to, rather than decomposing this unitary into C0s and a single qubit gate, how we can implement that directly with a arbitrary controlled phase gate. And so what you see here is our solution to that problem that then boils down on implementing two single qubit gates and one controlled arbitrary phase gate. And I'll tell you about how we realize this one controlled arbitrary phase gate. And you already see in this representation here, where I've just for simplicity assumed that every gate in the sequence of gates takes the exact same time, then you see that our direct gate implementation now takes a small fraction of the time of the decomposed gate implementation. And if your system has finite coherence, this will always be an advantage to end up with a better result at the end. Okay, and so here we would realize this variational parameter by controlling the phase of this controlled arbitrary phase gate, while in this decomposed version you would do that by controlling the rotation angle of your Z gate that you apply to one of your qubits. So that's this gamma variational parameter, and there's a second variational parameter which is called beta, and that stems from this mixing Hamiltonian or mixing unitary part. And the mixing unitary part in both the decomposed version and in the direct version is the same, so that we have not touched. And rather than applying the X operation, the mixing operator directly to our qubits, we actually chose to apply a virtual Z-gate to our qubits. And the main reason for that is that we chose not to calibrate a continuous angle qubit rotation in our system. And instead we chose to apply a combination of 2 pi-half pulses, like 2 pi-half pulses around the y-axis, and then do a so-called virtual Z-gate on our individual qubits. And this combination of 2 pi-half pulses in the virtual Z-gate effectively gives us a controlled angle x rotation on our qubits. But that we have applied in the same way, both in the decomposed version and in the non-decomposed version. Okay, so how do we implement our single and 2 qubit gates in our system? So our superconducting qubits have a number of levels. There's the computational states 0 and 1, and there's non-computational states above that, higher excited ones like 2, 3 and higher. And sort of the transitions between the computational states and the non-computational states we drive by applying microwave pulses to our qubits. And I'd explained to you on my title slide that that happens through these pink colored microwave frequency drive lines. And so here you see an example for how that then acts on our single qubits. So that's a single qubit state represented on a Bloch sphere. And if you control the length or the amplitude of the pulse, you can prepare an equal superposition state. If you double the amplitude of the pulse, you can invert the qubit state, or further increasing the amplitude of the pulse will bring the qubit back to its original state. And you can rotate single qubit states about different axes by changing the phase of that microwave frequency pulse. And what you see here is actually measurements that were performed, tomographic measurements on an individual qubit. And on the right-hand side, you see both the density matrix of a single qubit and the expectation value of the Pauli matrices for these qubit states. And single qubit operations in superconducting circuits can typically be done very well, and the errors are usually much less than 1% per gate. Okay, so single qubit gates are easy and work with high fidelity. So how do we do the 2 qubit gates? 2 qubit gates are, one way to do 2 qubit gates is to use one of these auxiliary states of superconducting qubits. So here we consider this 2 qubits, a qubit A and a qubit B, and we consider one of the 2 qubits to be in its second excited state. And we can bring that second excited state by tuning the qubit transition frequency into resonance with a state where both qubits are in the first excited state. And when that resonance is achieved, the 2 states can exchange their populations. And this population exchange, if it's tuned up right, can lead to a controlled phase gate with a controlled pi phase angle. So here's another little more detailed look at that, where I show to you this 2 qubit operation for the controlled phase gate. So you bring 2, 0 and 1, 1 into resonance. The interaction between the 2 states will exchange the population. And when the population comes back to 1, 1, you've actually accumulated a phase factor of -1. And what you can see is that none of the other states, neither 0, 0, nor 0, 1, nor 1, 0, got in resonance with anything else. So those have not accumulated any 2 qubit phase factor. And the combination of these effects then leads to this unitary that realizes a C phase gate with a pi angle, creating this -1 phase factor in front of the -1, 1 state. And so that's the unitary that goes along with that. So that C phase gate is represented by pictorially as you see here, and you can do process tomography and measure the process matrix. And typically if you tune things up nicely, then you get gate fidelities around 99%. And to get better than that, you have to put in some extra work. And you can turn these phase gates into C0 gates by augmenting them with these 2 single qubit rotations on one of the 2 qubits. So, but you can now play an interesting trick to not only have this 2-qubit gate being executed with a fixed pi angle, but you can vary that conditional phase angle. And that variation of the conditional phase angle can be achieved in the following way, namely by detuning this 1-1 state by an amount delta relative to the 2-0 state. And what then happens is shown here on the right-hand side in this plot. So what we control is both the length and the time, or the time and the amplitude of a pulse, which we use to bring the 2 qubits into resonance with each other, like the qubit A and the qubit B. And now we choose to not bring them exactly on resonance, but maintain a little detuning delta. And then what typically would happen is that you don't recover all of the population out of your 2-0 state. And to do that, you need to adjust both the amplitude and the length of the pulse in a concerted fashion. And that is shown here. Yeah? So here's in this plot here, you see a population diagram of this 1-1 state. And what you want to achieve is that the population of the 1-1 state is maximum, because that means that no population is left behind in the 2-0 state. And now if you change the amplitude with which of the flux pulse that you apply to your qubit, you will control the detuning between this 1-1 and the 2-0 state. And if you adjust the length of that pulse for the appropriate period of time, you can actually make sure that you get all of your population out of the 2-0 state back to the 1-1 state. And on top of that, what you observe is that the conditional phase angle that you have accumulated now depends on the amplitude of your flux pulse applied to the qubit and the duration of it. And if that's tuned up nicely, you can now pick a conditional phase angle for your 2-qubit rotation. And that is the thing that then allows you to do an arbitrary phase gate directly, rather than decomposing it into 2 C0 gates and a single qubit gate. And that will save time in the end. But it demands a calibration of this continuous gate, and that's some extra work, and you have to figure out whether that pays off, that extra work. But we can show you that it does.
Andreas, a quick question on this. So are there other states that you have to worry not to leak into when you're doing this transfer?
I think this is the 2-0 one is the one that is the dominant one for leakage that you need to control. Yeah. And a typical problem also in realizing just regular CZ gates, even if you don't try to play with the phase, is that you don't get all of the population back. And then you've leaked out into sort of a non-computational state. And for example, for error correction, that is really bad, yeah, because your typical error correction schemes don't know how to deal with that even. So minimizing leakage is important. Yeah. But when it's tuned up well, in this variable phase gate, leakage is not more of a problem than it is in a fixed phase gate. It's all a matter of how well it's tuned up. Okay, so here's this device that we've used. You've seen it a number of times now. We put that device into a PC board that we've made. So you see there's our next generation PC board that also allows us to look at larger devices. That goes into a sample package into our cryostat. And here's a picture of our cryostat, and you need to sort of think about how to get your wires in and how to shield everything properly magnetically. And then you need to get yourself a bunch of electronics and run your experiment. And the device that we have used is actually one that we've also done an error detection experiment on, that is in this Nature Physics paper that I've mentioned before. And here you see the properties of the sample. Yeah, the coherences are decent, yeah, somewhere between, maybe the lower ones are around 8 or 9 microseconds, and the larger ones are around 15 microseconds. So that's not stellar. There's labs which have better numbers there, but it was pretty homogeneous across the chip, and therefore it worked quite nicely. And one of the aspects that our lab is also particularly good at is qubit readout, and also joint qubit readout. So we can read out all these 7 qubits on this device with fidelities that are in excess of 98% and relatively small times, which is also important for error correction. And then we've characterized the fidelity with which we can do single qubit gates and also 2 qubit gates with fixed phase angle between any pair of these qubits on this device. And this data set, which you see here, was for fixed 2-qubit rotation conditional phase angle, but we've done these characterizations also for the variable angles. So now we can look at the problem that we have identified to solve with the QAOA approach. So here's our 7-qubit chip with this double diamond structure that I've mentioned. And we've done 2 sets of experiments, one on these 3 qubits shown in this dashed line, and then one with all 7 qubits. And the problem we looked at is the so-called exact cover problem. It's an NP-complete problem, and here's a really basic toy model, and I try to describe it. And so here you see this matrix, which sometimes is called the incidence matrix. And the goal of this exact cover problem is to find a combination of columns. Yeah, so you see columns here, such that when you pick any combination of columns, each row is covered exactly once. And you could look at this matrix and wonder what the solutions are. And here's another example. This is a 3-qubit example, and here's a 7-qubit example. Here you again see this incidence matrix, and the question is, which columns do you pick so that each row has only a single dot? And when you look at that, you obviously see one solution is, okay, you pick columns A1 and A2, that covers every row exactly once, or you pick column B2 on its own. And similarly in C, you can pick columns A1 to A4 to cover every row once, or columns B1 to B3 to cover every row once. And for this particular, these are 2 special problem instances which are compatible with the connectivity graph of our device. And for that, you need to construct this cost Hamiltonian, this Ising Hamiltonian. And the Ising Hamiltonian for this 3-qubit example is shown here. And the Ising Hamiltonian for the 7-qubit example is shown in the second line. And here I and J run over the edges of the problem graph defined by this incidence matrix, which needs to be compatible to the edges that connect the qubit layout graph in the device that we've looked at. And these the problem that we choose, if you can't do swaps or if you don't want to do swaps, has to be compatible with the connectivity of your qubits. Okay, and then we are ready to run this QAOA algorithm, both in the 3 and in the 7-qubit example. So here's the 3 qubits that we chose for the 3-qubit example. So I told you that now we can do just one controlled arbitrary phase gate per 2-qubit interaction. So that requires only two 2-qubit gates for one layer. So here we can count the gates. So there's 2 2-qubit gates, 9 single-qubit gates, which are the pulses that you see here. And then there's 7 of these virtual Z gates. These are the ones that we use in the context of our mixing Hamiltonian. And here you see the decomposed version, when you wouldn't use this controlled arbitrary phase gate, but decompose it into a C0 and a single qubit rotation. And that takes much longer. You see it already. Instead of taking maybe 300 nanoseconds, it takes more than a microsecond. And the total gate count is also much larger when you do this decomposition. And already here you see that you should expect the shorter sequence to perform better. And then you can wonder how that scales when you increase the number of layers, which was what we wanted to do in this particular experiment. Okay, and then we started to run our QAOA algorithm. So you remember, and we first looked at it for a single layer for 3 qubits. So in the single layer, you have only 2 variational parameters, gamma 1 and beta 1. Yeah, gamma 1 was the phase separation and beta 1 was the mixing parameter. And what you see on the left-hand side is there we've scanned both parameters explicitly on a 45 by 45 grid. So for more than 2,000 pairs of gamma 1 and beta 1. And we've measured the expectation value of the cost function. And you get this cost function landscape. And on the left-hand side, you see the measured cost function landscape. On the right-hand side, the simulated cost function landscape. And at every value of this 2,000 parameter pairs, we've performed 20,000 single shot measurements of our qubit states at the end of the operation. And we've also not done that only on 2 levels, but on all 3 levels. so that we could detect leakage. And that allows us to reject leakage, which would lead to errors in the algorithm. And so you can then, so one of the things that we've actually spent some time in was to try to understand these cost function landscapes. And by looking at the Hamiltonian, you can understand some of the features. Yeah, you find that the cost function is, for example, pi-half periodic in beta and 2-pi periodic in gamma for this particular problem. And there are certain symmetries, like a point symmetry about the center of the period, that you could identify, and that will then set over which range you need to scan these the two parameters to find all the results. And then what you also see is that there's minima and maxima in this cost function, and what you want to do is you want to minimize the cost function to find a ground state of that Hamiltonian, and the cost function is minimized at this dark blue spot that you see here, that I point to with my mouse. And overall, you see that the left-hand side is a measurement for a single layer, and the right-hand side there is a simulation for a single layer, and you find good agreement generally with a master equation simulation. And you see a little bit of difference here in this region there, and we could identify that where that comes from, and that's actually due to a little bit of residual ZZ coupling in our device that is present even when we don't intend to operate our 2-qubit gate. And that stems from a finite coupling that exists when the qubits are at their maximal detuning. Okay, and then we looked at that. So this was just scanning the parameters, but in a QAOA algorithm, you want to optimize over these parameters. So we've done a few optimization runs, and to do so, we started at a random point in this parameter space, and then ran a Nelder-Mead optimization algorithm, and to see whether we would find the global minimum. And so, for example, here you see what happened in the separation angle gamma and in the mixing angle beta. And when we would start in a random combination of gamma and beta, and then run Nelder-Mead. And as you run it for about 50 steps or so, you see that the Nelder-Mead then converges many of the times towards a single value of gamma and a single value of beta. And as you see, like the value of gamma and beta then points towards the minimum in the cost function, and that is what you want. And you can follow how you approach the minimum in the cost function as you go through the iterations of your optimization algorithm. And what you also notice is in some instances you get trapped in one of these non-global minima, depending on where your starting point was when you use this Nelder-Mead approach. Mm-hmm. And so the cost function, then if you evaluate the average of the cost function, it's this dark line, and every individual instance, some of which you reach the overall global minimum for this one cost function. And what you also see is that there's a good agreement between the data and the master equation simulation for this single layer. Good, so we're getting towards it. So there's maybe two things to note. So one aspect to note is that even the simulation doesn't reach the global minimum of this cost function or the problem Hamiltonian. And the reason for that is that a single layer will never be able to do that. In this particular problem, you need at least 3 layers to reach the absolute minimum of the cost function. And that motivated us to then try to run this algorithm for multiple layers with multiple variational parameters. And so the result of that you see then here. So we've then ran the experiment by starting the optimization algorithm at a point which was already close to the optimal parameters to investigate this depth dependence, this number of layer dependence. And we've done again 20,000 measurements at each value. And then at the end, we've looked at our qubit output register. And so here for this 3-qubit example, you see the different output qubit states for one layer p equal 1. And you see that there's 2 state combinations come up with the largest probabilities, namely 0, 0, 1 and 1, 1, 0. And you see that there's also probabilities at some of the other states. And if you increase the number of layers, as you should see in a second, go to p equal 2 or p equal 3, what you see is that the probabilities in the unwanted states get reduced and the probabilities in the wanted states increase. And the second effect that you also observe is that then the measurement results, which are these colored bars, the fidelities of those with respect to the ideal results reduce as you increase the number of layers. Yeah? And that's also clear because as you increase the number of layers, the protocol gets longer and decoherence affects you more. So the actual fidelity reduces from 98 to 95 to 86% relative to the ideal state. But still for 3 layers, the overall probability of identifying the solution state is larger when you increase the number of layers from 1 to 3. And we've looked at the same thing for the decomposed version, and that's this green data set. And the decomposed version is just worse because it takes longer. And you can stare at this a little bit more, but because I'm already quite a bit over my allotted time, or so I'll probably cut it a bit short here. So the decomposed version is worse because of the longer sequence of gates that you need to apply to achieve the same task. And so we've done the same thing on a 7-qubit instance, but the 7-qubit instance has then 2 to the 7, namely 128 different states. And you would probably not wish to directly look at this plot for these 128 different states. Okay, so this is my last data slide. So then how do you summarize this result in a meaningful way? So what we thought of was to plot the enhancement of the success probability. So what is this enhancement? So there's a probability for identifying the solution state correctly. That's what you want. And then there's a uniform probability distribution. For example, you could ask yourself, if I was just guessing, what would be the likelihood? Mm-hmm. And that's the baseline, essentially, this just guessing. And you could ask yourself, okay, how much better am I than just guessing? And plot that versus the number of layers that you run your algorithm for. And that's actually shown in this plot here. So there's this, like the baseline 1, the red dashed line is just guessing. And then you do your QAOA either in the decomposed version, which is the green data, in the direct version with this continuous gate set, which is the blue data. And the black boxes are just ideal simulations of the QAOA algorithm, which reaches a unity after 3 layers. And what you see here is that as you increase the number of layers, it gets better until decoherence gets you. And both for the decomposed and for the non-decomposed version, for 2 layers, it's better than for 1 layer. But for 3 layers already for the decomposed version, the success probability is less. And you see overall that the direct version, the controlled arbitrary phase gate, is better everywhere than the decomposed version. And the main reason for that is because in any instance, it takes much less time. It takes about 3 times less time than the decomposed version. And so we've also looked at that for the 7-qubit instance. And I've not shown you the details of that. But for the 7-qubit instance, guessing is even worse. Yeah? So your probability of just finding the right state by guessing is really bad. And you get a larger improvement by running a QAOA. And what you see there also is that the direct implementation is separated quite well from the decomposed implementation, just because it makes better use of your resources and is less affected by the decoherence then. Okay, so sorry for being quite a bit longer than I had hoped for. So maybe to sum this up, so we've implemented this continuous arbitrary phase gate, and it allows us to efficiently implement a QAOA with much shorter time than in the decomposed version, and that leads to higher probability of finding the solution state in a QAOA setup. And we've demonstrated that in an exact cover problem, both on 3 and on 7 qubits. And the largest number of gates that we've implemented in this multi-layer approach was about 400 on a 7-qubit device. And we're looking forward to try that on larger future devices as we move forward. Yeah, and with that, I'd like to wrap this up and maybe move to my summary slide, my thank you slide to our team, since this is the summary slide. I'll not discuss the Outlook questions, which were anyhow, I think, were optional. So I'd like to finish with thanking our team at ETH, who's put a nice effort into bringing this device up, first for a quantum error detection experiment and then for this QAOA experiment, which we did in the last half year or so. All right. So thank you very much for your attention.
Thank you, Andreas. Thanks for really broad and interesting talk in both the introductory part and the analyzed part. We can take a couple of questions from the audience now. I know you have another thing to do soon. One thing that if you go back to the slide with the P's, with the layers, how many layers did you manage to do in the seventh, I think, 3 or 4, the last slide on the, okay, that one. So you go up to 6.
Yeah, so for in the 3 qubit instance, we've done up to 9 layers,
much deeper, yeah.
And then on the in the 7 qubit instance, we've gone up to 6 layers, yeah, and then. But in principle, it doesn't. Once you've identified that your success probability goes down again, or so, it does not make sense to move on much.
Most
further.
Experiments. Even the recent Google experiment on this fully connected, or the MaxCat and the SK model. I think they managed to do maximally 1 layer for 23 qubits, or 2 layers, I think.
Yeah. This was one thing that we were really interested in for doing in this setup, was to actually look at the depth dependence, have a good shot at looking at the depth dependence, and you one of the results that you see is that with this particular using this more efficient gate set, we can go much deeper in depth than with using
fewer gates. Yeah, it's very nice. We have been looking at this, actually. I can tell you a little bit afterwards if you have a few more minutes. And I mean, the big problem with QAOA and all these approaches is that you need, except you need deep layers, you need to implement the Hamiltonian, which is also very hard. And if you go variationally, okay, you don't have to implement the Hamiltonian, but you still, in most of these optimization approaches, you need as many variables as qubits, and that doesn't scale very well. So we have been looking at this recently. We just put a paper out on even doing some sort of mean field logarithmic number of variables into qubits for certain problems. And you could, for example, solve 42 variables with 8 qubits. In sparse matrices, in sparse problem, and go up to maybe even higher, and depending or lower if it's the dense matrix. There's some sort of systematic way how to include correlations as you go up, without having to do the full one-to-one mapping that usually these things are doing. But let me see if maybe we can. Are there questions? I think there was one earlier. That was about the reference.
People could also just raise their hands or switch on their microphones if you allow that.
May I ask a question on?
Yeah, Mark, go ahead. Yeah. So Mark, just introduce yourselves and your group. I mean, this Mark is my postdoc, obviously, but there's one more.
Yeah. So I'm Mark. I'm a postdoc in Dimitri, Andreas. We've been talking a few times already. So seeing those results and also the Google results, so one thing that is clear is that, okay, so your approach of doing these gates differently help, but we see the challenges that it's quite difficult to go deep, P equal 3, for small systems and so on. So what is your general opinions in terms of the future of the scaling? Like if we want to start solving larger problems, and how do you see where it's going? Just a general question.
It is difficult. I think generally I think there's these very general scaling questions that Dimitris also just mentioned. Yeah, the number of variational parameters that you need to control for a size problem that you then would really be interested in. Yeah, there's also, I think there's new papers around that look at that and also ask the question, okay, say if you were to run something like that with error correction, yeah, and like how would things scale together? Would your advantage disappear if you were running error correction on top of that? I think there's a few systematic problems that one needs to look at. I think we're trying to address it from the experimental side. And trying to extend the reach of what we can do. And I think one of the aspects that we know already, we do tend to get samples with better coherences now. Yeah, so this one is so we have a bit of room there, and our gates will get somewhat faster, but it will not change orders of magnitude very, very rapidly. Yeah? So I think if there's clever methods that allow one to keep the overhead under control, I think that is certainly something to look at.
Yeah, we have been looking at that, as I mentioned earlier. We'll just put something on the archive. There is one question by our actually incoming new director, Jose Ignacio Latorre. Should I'll just read it, Jose, or you want to?
Okay.
I see.
Hi, Andreas.
Hi.
No, my question is about how do you fix in practice in the experiment the gamma and the beta?
Yeah, so we did two different things, or like at the one layer level, yeah, we just ran the real Nelder-Mead optimization algorithm to find. We start with a random gamma and beta, and then we let the system run the minimizer and find the optimal gamma and beta for a single layer. And the data that I've showed that we could do that typically quite well in 50 steps or so. And maybe if one runs a more clever optimizer, then you could maybe do it in a little bit less steps. And then because that takes extra time, yeah, for the experiments with larger depth, we've chosen to start at gammas and betas. Yeah, then we need more gammas and betas, like one for every layer essentially. And we've started to look at that beforehand numerically and started off and then only optimize in a smaller region. So because we essentially we weren't patient enough to run the optimization algorithm, and also we weren't really interested in that particular question, but we wanted to look at performance versus depth. So we used Nelder-Mead and fully automated. We've only done it at one layer, and at multiple layers we've just run it on a limited scope. Yeah, we've maybe ran 5 or 6 or 10. I wouldn't even need to ask what the actual number was. Optimizations around a parameter set that we knew numerically should be a good starting point.
Yeah, you see, this is a critical point because for scaling, this is a mess, because any method based on a gradient will fail because the errors are such that the gradient that you compute is dominated by the fluctuation. So actually you are not minimizing but hovering over the solutions, right?
Yeah. Not just too shallow. Yeah?
So all the examples I know, people do a pre-computation, which is classical.
Yeah.
But, you know, for the real larger problems, this will be a difficulty.
And this is
I think so. Yeah. So here it was for one layer, which is maybe not the interesting case, or this was done fully free running, but for the multiple layers, as it was not the goal. I think we could probably do, if this was interesting, one could probably learn much about that just from numerical simulations, how it behaves, and it probably will do exactly what you say, and so it was just something that we hadn't looked at, but it would certainly be interesting to see, say, if you would run a multi-parameter QAOA and just see how it would actually perform in a real experiment.
I think also the Google experiment, they also did the numerical calculation first and kind of trying to get it as guide for the rest.
Well, there are two solutions that can be explored. One is to use genetic algorithms, which are not related to gradients. And second is to use the scheduling, which is proposed by adiabatic evolution, which is, there is the typical curve, which is first very fast, then slow, and then very fast. And this has been proven to optimize this kind of evolution in general. You use really the adiabatic theorem for that tells you what is the gamma and the betas that you need at every step. So.
There is one more question from the audience, Rajesh. He says, what advantage do you have using gate-based over annealing for a combinatoric optimization problem? What advantage do you have using gate-based over annealing?
No, I do understand it. It's probably a question for one of the theorists in the audience. Yeah, probably Jose can answer that well. I think the QAOA is inspired by the annealing problem. It's, if I understand correctly, it's essentially a trotterized version of that.
Yeah. One answer is basically that you don't have to go slow. That's a major thing. In the annealing, you have to go slow. You don't want to close the gap. You have to go adiabatically down. And QAOA was suggested as an alternative to avoid that problem. As long as you could implement the Hamiltonian you're trying to get in and find the ground state and another Hamiltonian, which is easy to do, you quench back and forth, you do this back and forth layers, and then you get eventually where you want.
Dimitri, there is no classical efficient algorithm for 3-SAT. There is nothing you can write a circuit which would be replicating an efficient algorithm. So there is no such a thing as a gate base for this particular problem.
Yeah,
no?
for the
there is for the Fourier transform, there is for others, but not for 3-SAT.
Yeah, I'm talking about this quantum like Ising Hamiltonians type of stuff. For the classical
There's another question by Benjamin also.
Where is it?
I think he has raised his hand. Or
yeah, hi, I'm Benjamin. I'm a PhD student with Dimitri's group. So as I understand, you did 20,000 shots to evaluate the cost function once. Is that right?
Yes. So this is single shot readouts. Yeah. So at the end of the operation, yeah, we're getting the statistics. Yeah, and I'm not sure. I've not calculated what the minimum statistics needed to be for us to understand the result best. Yeah. If you look at what you in the end look at is these the probability distributions for the outcomes. Yeah. And you could ask yourself, what do you want to know about this probability distribution? Yeah, if there's zero error, yeah, and you would measure once, yeah, you would find one of the two solutions with probability a half in this particular example. At once you do 3 layers, and if there's no decoherence or no other errors, yeah. And the reason why we do many repeats is to essentially analyze the statistics of it and learn something about the errors, and whether 20,000 is already more than we need. I've not carefully looked at. Yeah, you could just look at what the statistics are in these different measurement outcomes.
My second question is like how long does like those 20,000 shots take? Is it done very quickly?
So a typical. It depends a bit on how we run our electronics. Yeah, I think and whether you use active reset or not. And for example, here you see on this slide, you see the duration of the longest sweeps. The 4 layers decomposed version took 8 microseconds. Yeah, and then if you do a measurement at the end, you can essentially do a reset, and that means you can, in principle, restart every 10 microseconds. Yeah, so you could run it at 100 kilohertz if your electronics holds up, and at 100 kilohertz it takes a fifth of a second, so 200 milliseconds to get your 20,000 shots. So this can be fast to get all the data.
There is one more question from Leonid. I know that we can't keep you for too long, but I think maybe it's the last one. From Leonid Krivitsky. Are there other uses beyond QIP of the superconducting circuits which you are developing? Other uses beyond quantum information processing?
Yeah, I think our own lab looks at a number of different things. So we do quantum optics experiments. So we've done a nice one which is out on the archive also is like, for example, creating entangled states of photons, looking at tensor network states, for example, that you could do. We're looking at distributing quantum information with microwave photons. You could look at, one of the things that I find really interesting is to use all the techniques that we have developed, which work really well. Yeah, we can do these quite complicated experiments already, but we can deploy these techniques also exploring the physics of other systems. So people have actually quite successfully been looking at quantum objects which also have microwave frequency transitions using circuit QED techniques. Yeah? And if you have access to tools like that, you can explore physics of other objects. And maybe the aspect that we've looked at ourselves most is looking at semiconductor quantum dots, where people are obviously also interested to realize quantum computers from them, but there continue to be sort of open basic science questions. And using the circuit QED or superconducting circuit-based techniques is typically very useful for that.
Okay. Anything else?
I mean, personally, I would have maybe another 15 minutes from now or so. That would probably also still
yes.
work.
If you have 10 minutes, it would be good to just chat. Thank you, everybody. Thanks for joining again this session. Next session, I think, is in 2 weeks. I'll have to check the schedule. Will be announced. I think we have Dieter Jacks coming on theory from Oxford, and also somebody from Peter Choller's group will follow up in the next few weeks, mixing theory experiments. I hope you guys enjoyed it. Thanks for joining, and see you at the next iteration. I'll email,
Thanks for listening.
I'll email some of you guys if you want to join the follow-up short chat with Andreas now. Bye.
All right. Thank you very much for attending this talk.